we have W being a member of having some property like an even number of zeros or something, and has also that has at least 3 ones, for example. So it has multiple properties. Actually, let's look at that. So let's say that W in 0, 1 star such that W has exactly 2 zeros and at least 3 ones. So that could be a language that we can consider. So what do we want to prove about languages like this?
Regular?
That it's regular, right. So, and what does regular language mean?
You can create a DFA out of it.
Create a DFA out of it. So if we want to figure out how to make a DFA out of this, well, could we say, well, let's make a DFA for the first piece, the exactly 2 zeros piece, and then make another DFA for the at least 3 ones piece, and then if regular languages are closed under intersection, can I make a DFA for this whole thing? Yeah. What if I wanted, instead of and, I wanted or? And this is inclusive or, not exclusive or. So if I can prove that regular languages are closed under union, could I make a DFA for this entire thing? Yeah, because or is just union, and is just intersection. So let's actually look at union, because we'll actually get intersection for free out of that. So let's look at intersection. I want to show the following. Regular languages are closed under union. Because if we get that, we get this problem for free. Well, maybe not free, but cheap. So here's an idea that is not going to work. I'm telling you in advance. I'm giving you warning. It's not going to work. Okay? So picture the 2 DFAs here. So run the first machine on the input W. If it says accept, or it lands in a final state, should it belong to the union? This string belong to the union. So if at least one of the 2 machines says yes, should I say yes to the union? Yeah. So run the first machine on that string. If it says yes, great, we're done. If it says no, rerun the same string on the other machine. If it says yes, then it's in the union. If it says no, well, both machines said no, so it's not in the union. What's wrong with that idea? Seems reasonable, but what's wrong with it? Yeah. No, it is deterministic because each piece is a DFA, so it does the exact same thing every time.
For some input character, you decide on going into this DFA.
Oh, so something related to, well, if we have a DFA and we consume a character, could we go back? So once we consume the input on the first DFA, we're toast for the second DFA. Burnt toast. So what do we actually do then? Well, we only really have one chance of doing all the computation we need over that string. We can't go back, we can't restart. So what do we do? What, sorry? Oh, that sounds like a good idea. If we can combine them into one gigantic DFA, that might be good. Well, let's see. What could we do? Well, let's actually do an example that I have conveniently already made. So let's take these 2 examples. just to motivate the discussion. So this is not the proof, but it's motivation. And the other one is this one. So here are the two DFAs I want to consider for now. So let's consider the string 101. Is it in the union? Look at the first machine. What does it do on 101? It ends in accept state. So is it in the union? Yeah. Well, what about the R0? The second DFA. What does it do? It does the same, essentially the same thing. It goes to R1, back to R0, and then finally to R1. Well, if we only have one chance of working with this string 101, could we just keep track at the same time what state we are in both machines? So at the very start, what state are we in of both machines? Q0 and R0. So what we want to do is let's do the transitions at the same time so that we do the first transition at the same time, then the second one. So we do them in tandem so we don't have that issue of rerunning the string. So Q0 and R0, what does the first character take them to? What does the top one go to? Goes to Q1. Where does the bottom one go? Goes to R1. What does the 0 do? They go back on both machines, and then the 1 obviously takes them back again. So the idea is we're taking into account the two states that we are in and doing the transitions at the exact same time so that we don't have any issue. Okay, great. Well, let's actually prove this then. So let's let there be two DFAs. So I'm going to call the first one M1 with ones in the subscripts everywhere. And then M2 is the same idea but with a 2 in the subscript. B DFAs. Okay, so I'm just picking two arbitrary DFAs. Is this sufficient in terms of getting from regular language to DFAs? Yeah, because I'm picking two arbitrary DFAs here. So that corresponds to arbitrary regular languages. So if we can get a DFA for the union here, then we're all set. So what could we do? Well, going back to the example we had before, well, let's see. Could we potentially be in Q0 and R0 at the same time? Yeah, at the beginning we always are. What about Q0 and R1 at the same time? I'm saying in principle, could that happen? Yeah. What about the reverse, where we have Q1 and R0? Yeah. What about Q1, R1? Yeah. So one of my recommendations for whenever you make DFAs or machines or whatever is consider all of the possibilities that could occur. Make a state for each one of those possibilities. So how many possibilities of pairs of states could we have? 4, because there are 4 combinations here. Let's make 4 states then. So we have a Q0. Let's call one state Q0, R0. I'm just making a new DFA from this. And then let's make another one Q0, R1. And then over here, let's have the Q1 versions. Q1, R1. Oh, that's so that kind of works. Maybe then we can just put the transitions, putting the combinations to each other so that we can relate one to the other. What is the start state here? Or what should the start state be? Q0, R0, because those are the two start states in the original things. Because we're doing union here, what should the final states be? Well, if we land in Q1, do we care what the second DFA did? No. So anything with Q1 in it is a final state. So these three are. What about the second machine? So anything with R1 also should be final. So I'm going to make that guy final too. So I don't want to, for brevity of time, I don't want to write all 8 transitions that are going to happen. So let's just do one pair. Let's do the Q0, R0 state, the start state. What of the 4 states should that go to on input 0? So what did the first machine do on 0? It stayed in Q0, so it's definitely going to be one of the 2 Q0 states. What did the second machine do on 0? To R1. So what is the state that we should go to? Q0, R1. So that comes down here on 0. What about on 1? Where should that go? Yeah, Q1, R1, because we just follow the first one, and then we follow the second one wherever they go. Oh, the many places we'll go. Okay, and then you can fill out on your own time the other 6 transitions that can occur. Or you actually have to because they're DFAs. Anyway, let's go to the general case unless there are questions about the example. Yeah.
You just drew the other one there just to show what did you draw on the side for?
Oh, what, sorry?
The ones you drew on the side of the DFAs?
Yeah.
The right of the DFAs, would you draw just the
So this is the, so this right here will be a DFA eventually for the union of the original 2.
Oh, so that's if you did a union of 2 DFAs.
Yeah. That's the DFA we'll get out of it. Yeah. Other questions? Okay, I want to get through this. So let's see. Well, let's consider these 2 DFAs, and we're going to make a DFA M with no subscript, and every other piece with no subscript. So we're going to specify the 5 pieces of this DFA we're going to make in terms of the pieces of the original 2 DFAs. Well, how did we make the states before? Well, how did we make the Q0, R0, R1, whatever states? How did we make those? Yeah, all combinations where the first one comes from some state in the first DFA, and the second piece comes from the second DFA. Well, what do those look like to you? What? Not concatenation. It's actually the Cartesian product. So it's just the product of the 2 state sets from before. So Q here is going to be the states of the first one times the states of the second one. Pick any state out of the first machine and any state out of the second machine, put them together. So it's just Cartesian product here. I'm going to leave, again, the transition function to last to make it easier. Well, let's see. What are the elements of a Cartesian product? What are the actual elements themselves of any Cartesian product? The elements themselves. Well, if I muck up the order of Q2, let's just say I want to put first, and I put the order wrong, is that a different state? Yes. So the Cartesian products are ordered pairs, okay? So all of the states here, let's actually write this set out explicitly. So it's ordered pairs, Q1, Q2. So this is an ordered pair because I put parentheses on it, where Q1 comes from the first machine and Q2 comes from the second one. So it's kind of like concatenation, but here I'm enforcing the order. So Q1 appears first, Q2 appears first because it makes things a lot easier when we make the transitions later. Okay, great. So what are states in this machine? Structurally, what are they? What are the elements of Q here? It's a two-word phrase. It starts with or and ends in ers. Do you need more syllables? It starts with order and ends with ers. Ordered pairs. So all the states here are ordered pairs, okay? Not from a restaurant. You don't order pairs there. They're ordered pairs here. Well, let's see. What does Q0 then have to be? Because it's a state of this new machine. What does it structurally have to be? It's a two-word phrase that we just discussed. It has to be an ordered pair. So Q0 then has to be some ordered pair because all states in this machine are ordered pairs. Well, what should this start state be in terms of the original machines? What should go in the first coordinate? Q01, the start state of the first machine. Okay, so the start state of the first machine goes there. And what goes in the second one? Q02, as you might expect. Okay, great. Anyone lost? Don't be shy, it's okay. I feel for you. I had trouble when I first learned this stuff too. It's been 5.5 years now. It's been a while. So it took me around 5.5 years to get to proficient. So just tell yourself these proofs 100 times and you'll be almost 50% there. I'm kidding. Think about it at an intuitive level because that's the way that we're going to look at it from now on, but we want to actually state it precisely. So let's actually do the transition function. Well, in general, not just here, what does the transition function do? It takes what and what to what? Current state and input and outputs a state. What are states in this machine? Ordered pairs. So the state thing in here must be an ordered pair. Cool. So the state that we're considering must be an ordered pair, no matter what. So, but this is just an arbitrary state. I'm not considering anything about what the state is. It's just an arbitrary state. And we're going to consider an arbitrary character A. The A character might not be in the alphabet, but I'm just naming it something to actually be able to write it. Okay, well, let's see. Well, the transition function outputs a state. What are the states in this machine? You should be good at this. Ordered pairs, okay? So the result of this computation after applying a transition must be an ordered pair. And it's going to be a big ordered pair, so I'm going to leave some room. Well, let's see. Let's get an intuitive idea of what to do. In the machine on the right here, from the Q0, R0 state, how did we know what to do? Yeah, so we looked at both coordinates, Q0, R0. We figured out, let's just say on input 0 to make it concrete. We figured out, what did Q0 do on 0, on input 0? Well, we figured out, oh, it just went back to the same state. Then we looked at R0, and we figured out where did it go on 0, and we saw it went to R1. And then from those two decisions, we figured out what state to go to. But more importantly, we looked at the original transition functions to figure out what to do. The Q0 one, we looked at the first machine and figured out, oh, what did its transition function do? And the R0, we looked at the transition function, saw what it did. So what do I do here? Well, how do I figure out what goes in this first coordinate here? What machine should I look at the original transition function for the first coordinate? The first machine. And what is the name of the transition function in that case? Delta 1. Cool. So delta 1 goes here. Well, I'm looking at the original transition function, and I got to give it a state and an input. Well, what's the input in this case that I should consider? The input, not the state. The character A. So in both cases, I'm looking at the character A. Just like before, if we considered the 0 transition, we looked at 0 in both of the original machines. So in both cases, we're going to have the character be A. But in this case, what's the state? Q1. Yeah. So Q1 and A. So informally, we're at this ordered pair of states, figuring out where to go. We look at the first machine, saw what it did on the first state in the pair. So Q1, what did it do? Whatever it does, the transition function will tell me. So what do you think is going to go in the second coordinate of this ordered pair? Yeah, just insert a 2 everywhere. Instead of 1, it's a 2. So delta 2 of Q2 with an A. So all we're doing is look at this ordered pair, see, we're going to figure out where to go. We're going to look at each of the pieces independently. The first piece comes from the first machine, figure out what it did, put that in the first coordinate of the result. Look at the second machine, figure out what it did, and put it in the second coordinate. Does that make sense? Anyone lost? It's okay, I understand. If you're lost, there's something I need to clarify. Or if there are any questions. If you don't ask questions, I can't help you. If there are no questions, okay. Well, is this DFA fully specified, this M machine that we're making? Is it fully specified? No. More interestingly, are the 4 pieces that we've made so far, we did sigma because it's the same alphabet. The 4 pieces we specified, did they have anything to do with the union at all? Ah. So could I do the exact same thing, the 4 pieces exactly the same for intersection? Ah, isn't that really cool? You can prove a theorem and then get a bunch of other results for free out of it. So what changes between union and intersection here?
Final state.
The final states. So let's do the final states for union. So this is for union. So what are the states in this machine again? I promise it's the last time I ask. Ordered pairs. Well, what is the final, what is F here structurally? What is it? It's a set of states which are ordered pairs, right? So it's a set always. So it's a set where each state is an ordered pair. I need to redraw that. Q1, Q2. So remember, we're doing union here. So if Q1's a final state or Q2's a final state, are we done? Is that automatically a final state? For union. if Q1's final in the original machine, or Q2 is a final state in the original machine. Are we done? Cool. So how do I figure out that Q1's a final state or not? It's an element of its final states, which in this case is F1. So Q1 is a member of F1, or Q2 is an element of F2. And that's it. So this construction, because we're doing the product of the states, what do you think the construction's name is called? The product of the states. Should I emphasize it more? The product construction. So this is called the product construction. Because we're taking the states, doing a Cartesian product of them, and making a giant DFA out of it. Okay, well, what if I wanted intersection? Yeah, and. So that'd be an easy way to do it. So this would be for intersection. Oops. Intersection. Could I prove that more formally, though, for intersection? Let's just say we got union. How do I prove intersection? Anyone have any friends named Augustus? I do. His last name is De Morgan. He lived a long time ago, so the friendship has kind of died off a little bit. But anyone remember De Morgan? Was he famous for something? Yeah, De Morgan's laws. Oh, what did those tell us? It's something to do with union, yeah.
Is it like A and B equals not A or B?
Almost. So, De Morgan's laws. So remember, where would you find something like this?
Chapter 0.
Chapter 0. So if we have two sets really, and we want to do the intersection of them, what you do is you complement the original pieces, union them, and then complement the entire thing. So we complement A and B, union whatever that is, and then complement the entire thing. If we have union, do we have intersection from this? Yeah. Why? What else do we have? We have closure under complement. So if A and B are both regular, are not A and not B both regular? Yeah, because we have closure under complement. If we have union, is A bar union A bar regular? Yeah, because A bar and B bar are regular. Well, if the result of the union is regular, is the complement over the entire thing have it be regular? So in fact, we do get intersection once we get union. So it's not that we can just put and here. Intuitively, that makes sense. But we can prove it more formally that way. Cool. Any questions on product construction? So you'll be able to now do a lot of the homework because a lot of the questions are of the form this property or and this property. Okay? So you'll be able to do a lot of the questions that way. So that's actually really nice that we can build DFAs that are small and for each of the individual pieces and then combine them just using the product construction. But I want you to note something that's very fundamental to computer science. For this construction right here, does it require clever thought of what the original two DFAs are? Do we need to do some introspection on what they are and then make some decisions about what to do? No. Could a computer do this? So this process not only are they closed under an operation, which could be enough, in fact, there's an algorithm to do it. We can feed these to DFAs to a computer if you're using like JFlap or something, and out pops out the DFA that you need. Isn't that pretty cool? So in fact, you can just encode these two DFAs up here into a computer program and then just form the product construction without even looking at what the DFAs really do. All you need to do is look at the individual transitions and each of the pairs of states, and you're done. You don't need to do anything special here. You don't need to think about it, and you just need to write the program to actually do it. And there are many libraries to help you actually do this, which is quite awesome, and it reduces errors. So you don't have to do it yourself, but you can if you want.